All right. So in today's lecture, I want to talk about two topics. I want to talk about fracture in our 4-point bend flexure setup. So what that looks like and how it initiates and so forth. But then I also want to preview the SEM EDS component of the lab that we're going to do for compositional analysis. So I'll break up the video into two parts. And so the first one, we will talk about the fracture and 4-point bend. All right, so we've talked about the 4-point bend configuration and some of the similarities and differences with 3-point. And so this kind of diagram, this one specifically is for 3-point. You can see the 3 contact points. But the point I'm trying to get here for this aspect is when it's in this configuration, what we see is differences in the stress state when we're in bending, when we're in this flexure mode. And so as you kind of see here, the bottom portion is where it says there's max tension, and then that would mean that the top is under compression. So this has some implications, and this is just how we calculate flexural strength, but this has, and this is all for 3-point, so kind of disregard the actual values and so forth. But this has some implications for how fracture occurs when it does occur in our glass samples. So let me go ahead and go over to the camera so I can show you sort of a brief demonstration on this sort of setup. All right, so let me show you this brief demo. And so basically I've just got this sort of flexible ruler, and this is going to be my visual for what a 3 or 4-point bend test sample looks like, kind of to the extreme, because we can see it flex. So we can kind of imagine that my hands and my fingers are the contact points. So if I kind of orient them like this, my thumbs are at the bottom, those are my outer spans, and then my index fingers are at the top, and you can see that that's basically 4-point bend. And so if I load it, if I put force on it, then it's going to bend like this, right? So that's 4-point bend. If I wanted to do 3-point, I would just remove one of my index fingers. But let's do 4-point, right? So the exercise here to show what's happening is if I load this, right, I'm not going to break this ruler, mostly because I don't want to, but probably I can't. But if I load this, if I bend it, right, it kind of illustrates what's happening on the top and bottom of the ruler, right? On the top, where my index fingers are, you can imagine that the atoms in this metal ruler are getting compressed, right? Because if you kind of notice it, they're getting kind of squished together. If you think about this bending, those are getting squished, right? So that's compression at the top. And we know that ceramics are stronger in compression, so we wouldn't expect it to break here on top. So that's important. However, if we bend it, right, if the atoms on this side are compressing together because they're getting squished, you can imagine that, you know, the bottom portion's forced to get longer, right? And so the bottom of this ruler is under tension, so the cork part here. And so that's the portion where we do know, because ceramics are stronger in compression, they're weaker in tension. So the fracture and failure is going to occur on the bottom where we're under that tension. And the slide I just showed you showed that the max tension was in the middle. That was because 3-point bend has that maximum point right in the middle. However, for 4-point, it's anywhere between these two contact points, between my two index fingers. So anywhere in there, that's where there's max tension along this, because again, we're stretching out the atoms on the bottom side. So we have tension on the bottom, compression on the top, and that's important to failure that we're going to see in the slides to come. So if you want to test this out, just do this with a ruler or something on your own. You can even do any sort of like brittle rod-shaped thing, a pencil or rod-shaped pretzels, things like that, if you want to sort of break them. There's an example in the slides if you want to also see that. But you'll notice that things will always initiate from the bottom. All right, so let's continue to talk about the failure that's going to occur. So we've talked extensively about the glass material being brittle, and so we're going to talk exclusively about brittle fracture. And so just as a review, that's the type that's rapid, and it really fails without warning, so we can't really predict it because it happens so instantaneously. This is under tension, and we'll talk more specifically about bending, but this under tension, we notice that these types of fractures with brittle materials will be smooth and really perpendicular to the surface. Some of those characteristics will carry over to bending, but this is for tension. So rapid crack propagation, little to no plastic deformation, and that all results in failure without warning. All right, so I mentioned, this is a tensile sample, and it's very smooth, flat surface, which tells us that it's brittle. We don't see kind of that cup and cone that indicates plastic deformation. This is more akin to our glass fracture surfaces under bending, and we see different regions, but in general it's fairly smooth and flat in these regions, and again perpendicular to the loading direction. All right, so we've seen that these failures occur at some type of defect or crack, and so we can actually sort of trace the initiation, the crack, by looking at what are called chevron marks. So these are I believe impact samples, but it kind of much applies, but to the same as what we see with glass. But you can see these lines all sort of radiating out from a single point over here. And the same thing, there's a lot of lines that trace back to this point right here, and those help us sort of find the initiation crack point in samples. For us, we can get a little bit more specific for glass. So glass is an amorphous material, so it doesn't have grain boundaries and things like that. And so that will be different than polycrystalline or single crystalline materials that you'll see, because there's no grain boundaries to contend with. And so for us, what we see, and so basically you see it in this figure I showed in the previous slide, is there's an origin, the source of the failure. So most of the time this is a surface flaw, a surface pore or something. So you see that, and you can identify that because, again, these kind of markings, like those chevron marks, kind of tie back and radiate out from the central point of failure. And so oftentimes they're kind of small, but we can see them. And so we'll use the microscope in the lab to kind of identify the failure, or to look at some of the fracture surfaces for your glass, and you'll hopefully be able to see similar aspects to this. So that's the origin. And then out from there, we identify sort of a first region, which is this part or the part here. And this is the smoothest region. You don't really see any features there. And so we call this the mirror region, as you can see up here and over here. So this is the initial sort of acceleration of the flaw, of the crack propagation. So again, this is all happening very, very quickly. So it's initially accelerating from the origin, after which you'll see this little speckled region that you see here, or here. And so this is known as the mist region. So it basically kind of roughens the surface because the critical velocity has reached. So it's basically slowed down its acceleration. And so it's roughened the surface. And then afterwards, you'll see what's known as a hackle region, which is even rougher. And then this is where those striations radiate out from. And so you'll see that, and that's kind of what points you back towards the source of failure. So this is very common. Relative amounts of these regions can differ and be larger or smaller, but typically you will see these regions if you can identify the source of failure. All right, so let's look at more sort of macroscopic views of the fracture. And so if we look out kind of the side of the glass rod that we have, when it fails, we can tend to identify in general where the origin is down here. And again, because the bottom of the glass is under tension, we expect it to break somewhere on the bottom of the glass. So the origin's here. And then we see that sort of mirrored region. And then what we see, we didn't really get to this on the previous image, but we see this little curl up here. This is known as the cantilever curl. And this actually kind of identifies the portion that's under compression. So if you see this curl, that tells you that this region is compression. So it can actually help you identify top and bottom if your sample is not clearly identified. Although in this lab, we have tried to identify it as well as possible. So this is very common and also tells you about bending. So here's just another view from a different ASTM. And so the cantilever curl here not only tells you that this is the compressive side, but when you see that, it also means that there was tension on the other side, and therefore that combination tells you that there's a bending stress. So when you see this cantilever curl, it tells you something fractured under bending. So that's an important, if you don't know as much about it as we do. All right, so let's look a little bit more about the fracture patterns. So these are all what I would term typical or valid fractures that occur in 4-point flexure. So we have primary fractures. So these are the primary fractures, and you may notice the little curl at the end. So this is the top portion, and then the bottom arrow always indicates this where it initiates, so the bottom. So these are within the area of maximum tension between the smaller load points. And so these typically run at right angles to what they call the long axis. So you can see that this is, perpendicular to the long axis. So these are valid tests. And so these have a little cantilever curls. But also you can have the same thing happen, but you can have a much larger cantilever curl. So you see that this portion here, the fracture initiates here and roughly perpendicular to the surface. However, the curl is much larger, and so you can see it going up from there. And so this is also common and typical. Nothing crazy about that. And there's lots of kind of variations to these. Sometimes it even curls back down like this to get a secondary fracture. And if there's enough force, you can actually initiate a secondary break from the reverberations when the sample fractures. And so these are also valid. Nothing wrong with these secondary breaks, but this is caused from reverberations in the glass. So these are all valid tests. So when you're looking at your own samples, these are typical, and these are just variations of what can happen. So this was kind of a schematic showing you different breaks, but I wanted to show you some real samples and what they look like. So these are kind of the same, showing valid test and where the initiation points happen. They don't always happen right in the middle. They can happen along the length as well. And the origin doesn't have to be perfectly at the bottom of the rod, kind of like it is here. You'll notice sometimes that it happens over here. So, for example, if there's a relatively large flaw somewhere else, like over here, that can outweigh the fact that there's maximum tension at the bottom. So having some variation in the location of the origin is also possible. But I do want to move on to some sort of invalid fractures that can occur. And these are ones that happen when there's a fracture that occurs due to crushing at a contact point. So let's start with a more valid test. And so this is taken from the same ASTM where the other images are. And you see that we have the initiation indicated by the arrow right in the center. And then you see that these other marks. So these are the contact points for the setup. And so this one happens in the middle, away from those contact points. And so this is a valid test, this first one. So it's perpendicular to the surface, or sorry, perpendicular to the long axis, and it's right in the middle, so it's not caused by a contact point. However, we look at these other ones, the second, third, and fourth one down here, and you'll notice that the fracture occurred here, here, and here. So effectively, these have all happened right where there's a contact point, right? Not in the middle, but at a contact point, at the outer lines. And so these are all invalid tests because the fracture is occurring by at that contact point, which is not where it would indicate. It should. All right, so if we look a little bit more in detail on the same types of invalid test, we see that what this can kind of look like. So here, the white arrow, this is the primary fracture point. It started at this contact point, contact crack at the outer load point. But it also had another fracture or crack, this sort of cone that you see at the middle loading point. And so this just kind of shows you some of the different types of fracture, what fracture looks like a little bit differently here when it's based on these contact points.